Hello, my name is Chris Britton, and I'm a PhD candidate in the Edge Lab at Princeton. Over the next few minutes, I'd like to give you an overview of our work on social learning networks, efficiency optimization for MOOC forums. This is joint work with Swapna Mukhopadhyay at IBM, Felix Wong at Yelp, and Liang Zheng, Meng Chang, and Vincent Poor at Princeton. A social learning network, or SLN, encapsulates a range of scenarios in which a number of people learn from one another through structured interaction. These are networks that exist between learners, instructors, and also modules of information. The proliferation of online learning and online communication in general has given rise to a number of SLN applications. Some of these include online education, enterprise social networks for online training, and Q&A sites, which have created SLN among students, employees, and askers-answerers, respectively. In recent years, the average SLN has started to get much larger, with courses like Massive Open Online Courses, or MOOCs for short, having scaled enrollment to tens and hundreds of thousands of students in single sessions. While broadening access to education on a global scale, the small teacher-to-student ratios and asynchronous nature of interaction in these courses are just two of the reasons why it is difficult to achieve efficacy in these scenarios by traditional means. For example, the teachers cannot personalize their instruction to cater to each of the students as they can in a brick-and-mortar classroom. As the one scalable component of online learning, SLN becomes critical to achieving effective learning in these scenarios. In this work, we are developing ways of optimizing the efficiency of communication between learners in an SLN. To do so, we have started by asking three fundamental questions. First, how should we define the ideal SLN? Second, how efficient is the observed SLN in comparison to the ideal? Third, what are the structural differences between the observed and optimal SLN that can form the basis for our method to improve the network? To study these questions, we have proposed a framework for modeling SLN efficiency. Our framework compares the benefit obtained by learners in the observed network to that which can theoretically be obtained through optimization. We model each learner individually as possessing certain levels of seeking or question-asking tendencies and disseminating or question-answering tendencies on a set of latent educational topics for the course. Additionally, we model the social structure of the SLN, which captures the level of connectivity between each pair of students. Taken together, this gives us a natural way of defining user benefit by analyzing the compatibility between the topical and structural aspects of a user's discussions. From this, our research methodology can be broken down into a few components. From the SLN discussions, we have to quantify the observed SLN between learners. Then, we have to determine the ideal SLN. The ideal SLN involves a few parts. First is topic extraction, in which we determine the sets of topics that the students are discussing from the text they have written to each other on the SLN. Second is parameter estimation, where we determine the parameters of each individual described above, their seeking and disseminating tendencies measured for each of the topics. Third is network optimization, in which we optimize the level of connectivity between the learners to best match the individual parameters. With the observed SLN and ideal SLN in hand, we can then proceed to answer the remainder of our research questions by performing an efficiency evaluation and comparing the properties of both networks. But before that, let's go into a little more detail about each of these blocks. For network identification, our problem boils down to coming up with a user-to-user graph to represent how learners are communicating. For MOOC and many other SLN applications, the communication occurs in a discussion forum. This can be represented as something like this, with learners on the left side, threads on the right, and the sequence of posts and comments written by learners as they appear and occur in each thread. There are several possibilities for how to map from this to a user-to-user network. For example, we could treat this as a bi-party graph and measure co-participation counts between learners. For studying SLN efficiency, though, we need the graph to preserve how learners are responding to and communicating with each other. In particular, we want the graph to be directed, weighted, and non-symmetric. After all, if Alice responds to Bob's questions with a certain frequency, that doesn't necessarily tell us anything about how often, if at all, Bob will respond to Alice. As a result, we define WUV as the probability that learner U will respond to learner V when V makes a post. There are many other considerations too, and you can check out the full version of the paper given at the end of this video if you're interested. For topic extraction, there are many standard algorithms in information retrieval, like TF-IDF and LDA. We use LDA, or latent Dirichlet allocation, which is a generative model that has been applied to extract topics from discussion forums in several prior works before. In our application, LDA models each post as a distribution over topics, and each topic as a distribution over words that appear in the forums. Qualitatively, we observe reasonable outputs in applying LDA to our datasets. For example, in an algorithms course, these are the top 3 words we get for 4 of the topics. This topic, for example, is clearly about network graphs. For parameter estimation, we analyze the learner's tendencies for seeking, or asking questions, and disseminating, or answering questions, on each of the discussion topics. There are a couple of considerations to be made here. To start, how can we determine whether each post is meant as a question or as an answer to a question? Then, what is the right way to aggregate all of the questions and answers together for each learner to come up with their seeking and disseminating tendencies? For more details on our approaches for these questions, again, you can take a look at the full paper. With these tendencies in hand, we can then model how much utility each learner is getting from the network. We identify 2 ways in which each user can gain benefit. First is more obvious, from learning. A user's utility is higher when she has more incoming dissemination from her neighbors on topics that she has high seeking tendency for. Second is less obvious but also important, from teaching. Something that is well discussed in literature on education, we can all relate to the fact that people learn by teaching others. In this component, a user's utility is higher when she has more outgoing dissemination to her neighbors on the topics that her neighbors have high seeking tendencies for. Taken together, these 2 components define a user's local utility from the SLN. The final component of defining the ideal SLN is network optimization. Here, we want to maximize the global utility in the network, which is the aggregation of the local utilities just discussed. This optimization has some constraints on preserving the individual local utilities, with parameters controlling exactly how much of the utilities are allowed to decrease from the observed network. It also has some practical constraints, like on limiting a learner's level of participation to what she can handle. This is particularly important in MOOC, where people can have very different schedules and time constraints. Our variable in this problem, as discussed, is the user-to-user matrix. The resulting optimization problem is convex, which makes it solvable in theory using standard off-the-shelf methods. However, we're optimizing over the full user-to-user network. With even 1,000 learners, which is among the smallest of our datasets, this problem will have over millions of variables. Therefore, we derive a more efficient projected gradient descent algorithm in which the steps of computing the gradient and moving in its direction, projecting onto the feasible region, and recomputing the objective are repeated until the algorithm converges. Now we move on to efficiency evaluation. We consider 4 datasets, 2 from quantitative type courses, algorithms and machine learning, and 2 from literature type courses, composition and Shakespeare. This graph plots the fraction of utility obtained in the observed SLN relative to the utility obtained in the optimal SLN. Along the horizontal axis, we vary the importance that is placed on teaching relative to learning in a user's local utility. On the left, the teaching benefit is not included at all, whereas on the right, teaching is just as important as learning. For each of the courses, we can see that the efficiencies are rather low across the board, from about 68% at the lowest to about 82% at the highest. This indicates that there are a lot of potential benefits to be gained through optimization. We can also see that efficiencies tend to decrease as more of an emphasis is placed on teaching benefit, which indicates that networks tend to form naturally more around learning rather than teaching benefit. There are a number of comparisons we can do to see the structural differences between the observed and optimized SLNs. One is to look at the differences between the outgoing degree distributions. We show that here for each of the datasets. The solid lines are for the observed SLN, and the dotted lines are for the optimized versions. What we can see is that the tails of the distributions get smaller after optimization because there are less learners that have large outgoing degrees. In other words, optimization tends to make participation more uniform so that learners are gathering their information from more people. So, the optimal network tends to improve global network utility, resulting in a social learning network that is more distributed in participation. But what about the local utilities for each of the users? Here, we show a comparison between the local utilities in the observed network on the horizontal axis and in the optimized network on the vertical axis. What we can see is that in addition to improving efficiency, optimization actually improves the local utilities for the majority of users too, with most people falling above the equality line. If you are interested in the algorithm details, a more comprehensive set of results, and how we are transferring this to practice, feel free to check out our paper published in Infocom 2016, available at the link shown here. Also, my contact information is given. Feel free to email me at cbrinton@princeton.edu to discuss further. Thank you for watching.